we have a battle going on here with temperature. This is Northwest Nuclear Laboratories. We're working on a fusion reactor, and we've just done a series of experiments with neutron output, which point to the fact that the temperature of the reactor vessel has a great deal to do with the neutron output. And we've calculated a slope for that and related it to temperature. We have not done a repeatability and reliability study to determine whether or not we always have a correlation between a set temperature and a set neutron output. That's still in front of us to do, but clearly we know that temperature is affecting our output. So in order to be able to collect relevant, stable data, we have to rigidly control our temperature for the reactor vessel. To do that, we're going to have to install a matrix of water blocks. Now, those are some interesting little guys that look like this. Can you all see a copper water block?
Yes.
Okay. So these are pretty little guys, and the back is very shiny, and it's also been milled. It has a very, you can actually see the milling tracks across it. Someone has run a very precision instrument on this to get an absolutely flat surface. The rest of it is brushed copper. And what's interesting is as I examine the side of this thing, I don't see any seams. And what this tells me is that we started out with a slab of copper, and it is indeed about the weight of a chunk of pure copper. And then someone has drilled down into the slab and then burrowed around within the slab to create a chamber that will allow coolant to circulate. And then there's an inlet and an outlet. You decide which. I blew some compressed air through one of these and immediately had a stream of copper particles coming out the other side. So I understand that there's still a bunch of milling debris inside there. I went ahead and fired 125-pound PSI air through all of these to clean them out. And I ran that air until there was no more debris while I was vibrating the block, just to make sure that I dislodged anything that would ordinarily come loose with a bump. And so at this point, we've gotten the loose debris out of there, but that's not the only problem. These nozzles have been generously super glued in. Yep, you heard that right, super glue. I managed to pluck one out without much effort. And there are about 60 different problems with that. The first problem is that any kind of heating and cooling, this block is going to heat and cool at a different rate than this little nozzle. And so at points in time, the hole will exceed the size of the nozzle momentarily, and there will be some fracturing of the glue and eventually leaks. Leaks around a reactor vessel with 100,000 electrical volts is not a good safety formula. So you want to make sure that if you're going to use liquid cooling, that you've mitigated all of the leaks you possibly can, and indeed have put some rigor in safety. Because if that fluid starts flowing around and or to get down into the power supply, you're going to have a 4th of July in the middle of December. So we need to absolutely assure ourselves that these little guys aren't going to come loose. And to do that, we're going to solder them. And as you can see, I've already done one. And this is one that's properly done. And you can see that the solder is flowed freely and smoothly all around the base and up onto the pipe, such that the little lip and ridge is no longer visible anywhere. And that gives you assurance that the solder has bonded to the metal on both of these, and therefore your chance of having a leak is about zip and none. Very, very low. If there were significant vibration involved, you might develop some cracks in the solder, but that is not the case in this particular application. So bottom side is still smooth, and we have our machining marks, and the rest of it I have cleaned back up with a wire brush to get the residue from the soldering process off. And so this is the goal. This is where we're trying to go tonight. And we've got 7 more of these little nozzles that we're going to solder. So we're going to do this as a process and learn a bunch along the way. Now I have a little tripod ceramic insulator here. These used to be asbestos. I don't know what they are today. David, maybe you know?
I don't know what they are, but they're not asbestos anymore.
Okay.
Probably ceramic, like you said.
Okay, some kind of a clay ceramic. And they're high temp. And what we want to do is we want to take these and we want to solder them, but we do not want to mutilate the bottom of this, because this will be going directly up against the conflat. Now let's take a look at that. By the way, to keep you folks from getting seasick, if you want to watch the video on Google, it's a much smoother show. You'll have to continue to listen on Teams, but the video is very smooth. So, as you can see here, this is roughly how these are going to go in. There's going to be one here and one here and perhaps one up about here. So they fit between the center spout and the outside bolts. Now, pardon me while I get a little extra cable here. Are we still connected?
Yes.
Okay. This is a metal oxide thermal paste. And it comes in a little syringe. And this, when you paste this on the back of one of these and affix it to the machine, it makes a thermally conductive surface that will transfer the heat. And we have one of these for each of the 3 water blocks. And so we'll be applying that.
Is that a permanent bond?
We're doing 2 things to bond the water blocks to the reactor. I have an epoxy that is being shipped to us, and it has a very high thermal transfer component. And so what I intend to do is put a little dot of that thermal paste in the center and then smush it up against the reactor, and then we'll run a bead of the epoxy around the outside of the water block, gluing it into place with the cavity, if you can call it that, full of this thermal paste. So we have the highest possible heat transfer between the conflat and the water block. And with 3 of these, they're 40 millimeters by 40 millimeters. You're going to have 360 millimeters, roughly, of surface area covered on that conflat. So that should be more than enough to bring the temperature down. In our initial optimum temperature that we're shooting for is about 100 degrees. If you examine the chart that Christina sent out, you will see that there is a very steep fall in neutron production starting at about 80 degrees and going down to 100. And then there's a sharp knee, and the degradation seems to fall off, changes the rate at which it slows down, and we'd like to catch it right at that knee. And the reason is we would rather be south of that knee than north of it. That is to say, we would rather be somewhere between 100 and 120 degrees than 80 and 100 degrees. And the reason is because a small change in temperature in the 90-degree region is going to precipitate a significantly larger change in the output of neutrons than a change in the area between 100 and 120. So we want to come down to the less sensitive area and try to find an optimal zone to operate in there. We have good neutron output, but the measurements that we're making right now require stability. So for the sake of these measurements, we'll shoot for a temperature around 110 degrees at the most. 105 would be optimal. Later on, we want to get serious with the refrigeration because, again, we didn't see a top to this. And now the question is, well, gee whiz, what happens at 60 degrees, 50 degrees, 40 degrees? What then? Well, we don't know. And to get the answer to those questions, we're going to have some heavier duty refrigeration, I think, than we have today. That's okay. It's actually a few $100s. It's not big bucks because people have saltwater aquariums. And a chiller for a saltwater aquarium that runs about 40 degrees is actually relatively inexpensive. And it would be perfect for the kind of work that we're doing. And it's designed to hold a very specific rigid temperature. Why? Because the marine life that it protects has a very narrow thermal band for their health and survival. And so one of the things that the manufacturers found entering that market and trying to make chillers for saltwater aquariums was that they had to be able to offer their customers very rigid temperature control. Gee, isn't that nice? That's exactly what we need. So we've got a couple of things playing into the mix for us that are going to work out really well. Okay, this isn't going to take the whole 2 hours tonight by any stretch of the means, but we're going to move along here and hopefully show you some soldering. This is the first time that we've tried to do head cam work on the solder bench, and I'm going to try not to jerk my head all over everywhere because I know that's going to make you seasick, but we'll go through some things here that hopefully if you ever have to do some serious soldering, you can rely on some of the information to get the job done. Okay, I'm going to go after a solder block that I haven't done yet. Yeah, I am. And we're going to take this from scratch. So I'm going to move from off of this twill gene to here, and then ultimately it's going to go down here into a chiller bucket, and then it's going to come back up here and sit on the twill gene again. And the reason for that is because this brick is very abrasive. And again, we want to preserve the back surface of this copper. This copper, you can actually make a dent in it with your fingernail. You can make a mark in this copper just by pushing on it. It's a very soft metal. And so we want to minimize the amount of damage we do to that surface, because that's the surface that is going to bond thermally to the conflat. So we will begin with some gloves. And the first thing that you have to deal with when you're thinking about doing some soldering is, as you can see, this solder has very nicely explode onto the metal. And to get solder to do that, solder responds to oil and grease the same way water does. It beads up. It won't stick. So the first thing we have to do is clean the solder block of all of the oil and grease. And the solder, the object you're going to solder may look absolutely clean to the naked eye, but oils in your skin can be all over this thing and play hob with a soldering job. So we're going to take a little bit of alcohol here and a little bit of Twilgene. And the alcohol I'm using is 70%. You should never, ever have anything of a higher concentration around a soldering bench than 70%. And the reason for that is because if it ignites, you don't want a hot flame. It's a lot harder when other materials start catching fire to deal with a situation if you've got a really hot fire going. And so 70% it's in, you know, you can get burned with it, but it takes a lot of time for alcohol at 70% to catch other materials on fire like wood and that. Now that wasn't smart, Carl, because we're trying to keep it off the brick. Okay, so I've cleaned this up here. Now the next thing we're going to do is we're going to use some soldering flux. And I have a watch glass here. These are really handy in chemistry. I don't know if you've heard this speech. Forgive me, Dave, if I'm intruding on your territory. But you can order these, and if you ever get into chemistry, I would suggest you do that. They're great for holding all kinds of powder and liquid in small quantities, a measure or two that you're going to use for a particular project, and you just have it out. In this case, we've got some liquid soldering flux. And we're going to take some of this liquid soldering flux, and we're going to put a few drops of it in this dish. And I'm just going to use a Q-tip. I'd like to conduct an investigation. You see that? I don't know why, but most of the boxes of Q-tips I've been getting lately are broken when I get them. I take them out of the box and they're already broken. I'd hate to have something like that stuck in my ear. You know, that's not a good thing.
What brand?
Okay, so.
What brand are you using?
I actually don't buy the Q-tips. Wife does, but they're Costco. I'm sure the generic brand. So, okay, so I am putting this solder flux around here. The flux reacts with the heat, and it also cleans the metal and prevents dirt and grime from getting into the solder operation. Now, in this particular solder project, I can get a little bit more on here. You have to think about what you're trying to accomplish, because we have a difficulty. We have a very, very thick piece of copper, and then we have these delicate little nozzles. these delicate little nozzles are going to heat up 100 times faster than the copper block. So long before the copper block is hot enough to solder, we could actually reach a temperature where these nozzles start to deform. So we don't want to go there. We want to heat the block and let the heat flow out, and we want the block to warm the nozzles. And in doing so, by using the block to warm the nozzles, we know that the nozzles will be approximately the same temperature at the block at any point in time. Now, this is the kind of solder we're going to use. This is Rosin Core. And I want to show you right alongside each other here. This is the kind of Rosin Core solder we would use for electrical work. As you can see, it's very, very thin, and it's appropriate for printed circuit boards and easy to control when you're soldering wires and things like that. This big, thick stuff is for plate soldering, the kind of thing that we're doing today. It's a little harder to find, but it also is hollow. It's inside. You can actually see a little black spot on the end there. That's not a black spot. That's actually a hole. This is a tube, and inside the tube is a rosin material that's a soldering flux. There's essentially two kinds of soldering flux. There's a rosin core and then something else called an acid core. The acid core, again, is for larger plate type soldering because it cleans more rigorously. The acid core, you don't want to use that on any kind of electrical connection because over time it tends to corrode and it can actually create electrical problems if it gets into switches and things like that. The flux is corrosive. So you don't want the flux around any kind of electrical work. The rosin core isn't a problem. So what we're doing here is we're going to apply some of this rosin. And I've got my little handy dandy torch. And this is a slick rig. It's point and shoot, one speed, but I don't have to fuss with it. I'm not having to tweak valves. I'm not having to start it. I don't have to click my spark thingy. I don't have any of that. I just hit it, and it's got a piezoelectric start, and away it goes. So there's a trick to this, and as you watch, I'm going to go ahead and set this back, and we'll have some excitement. And you can actually see the heat progress across the block. I'm putting a little solder on there just to kind of watch, see how it behaves. As you can see, it's starting to flow. That's what we want. Okay, we've got that one. Okay, that one looks really good. That one's all done, and we are done. Can't quite get a grip on this. Let's see if I can get one of the nozzles. We're just going to let it sit for a minute. You can see when I tap it that the reflection bounces. That means that the temperature of the block is still above the molten point of the solder. And we need to wait until the temperature drops below. Oh, I see a spot right there that we missed. We're going to have to go back and heat that guy up. See how it's okay? Got it that time. There's obviously an air pocket or something. It's giving chase here. I'm having difficulty with. Let me see if I can throw some. No, don't have any. We've exceeded the amount of solder I'm comfortable putting on it. Oh, we got it that time. If it'll just stay that way, we'll be fine. As you can see, the other one has now congealed. This one over here, well, not yet. Okay. It did what we wanted it to, but the problem is we've got an issue with cooling. Tell you what we're going to do. We're just going to abscond with this fan. Now I'm going to stand back about here because I don't want to put so much air on it that I blow that solder away. I just want to cool it down enough so that the solder congeals. David, how many people do we have watching?
We're only missing one right now.
Okay. Okay, this is working really well.
Would it work to place that on an ice cube in order to cool it quickly? Or would that cause a problem?
I think it would. And the reason for that is because the metal expands and contracts, and it's more likely that you're going to create cracks in the solder joint by thermal shock. And so, but looking at it right now, I would say we're past the point where it's congealed. I'll check it. Yeah, that's solid. and that's solid. Okay. Now, take our object, we'll give it a bath. Now, I don't know if you can see it or not, but I am looking at the bottom of the bucket, and you can see hot water moving away from the copper, and that tells you that it's still warm. And when you no longer see those variations, that's what tells you that you're dealing with something that's cooled down a lot. Now, I got it out. I'm looking at it. And the other thing I'm looking at right now is that it's wet. And why would that be important? Well, because if it stays wet for a while, it's probably fairly cold. And indeed it is. It's cold to the touch. That's a good thing. So now as we look at our solder work, we've got two very smoothly soldered, completely covers the area. And an interesting, yeah, it looks like we may have gotten a little solder up there. I didn't know we'd done that. Touched it momentarily, apparently, in the soldering, but it didn't change the size of the nozzle or anything. So that's no problem. Okay. So clean this up a little bit. And you can see the thermal lines, the different colors. And the thermal lines in the bottom are going to stay. Reason for that is because we're not going to attempt to brush the bottom. But there is, as you can see, this black stuff. That's flux. It's still on there. So what we're going to do is I have this. This is Flux Remover for PC boards, and it's great at getting rid of Rosin Core solder. So we're just going to hold this over the bucket, I think. You just kind of give this a little bit of a bath and a rub. And get rid of any excess rosin or soldering flux. Now, ordinarily I'd use a wire wheel, but for the sake of demonstration tonight, I'm just going to take a wire brush through here.
And the purpose of the wire brush
is cleaning the solder joint itself. If you look at the solder joint, now we've gotten all the rosin off of it, and it's real nice and clean and shiny. And we can turn it and observe that there are no leaks, no pinholes in the solder joint. And that's really important. The other one over here you can see is still pretty crusty, and I don't know as much about it because I can't see it clearly. So again, I'm going to take my wire brush. I'm going to clean that solder joint, pull any flux off of it so I can see the mechanical integrity of the connection. As you can see, we do have an imperfection here. It's right there. Now, I can't tell whether that's a pocket or something else, but there is a, can you folks see the little dot right at the base of my finger?
I think so.
Come up a little more, see if it's, I don't come up anymore because it'll just get fuzzy. Okay. A very, very small, looks like a divot though. It does not look like it goes all the way through. So I will explore it. What I've got here is a little poker. I'll stand in some really bright light and just work my poker down into it. Yeah, it doesn't even go down a quarter of an inch. That's not a hole. That's an ablation in the material. So if that's the case, we should be able to take a fine edge file and using the edge of it, file that smooth. Okay, so came off. So that's watertight. Okay, so one down. Questions or comments? Awful quiet out there. Alex, you watching this?
Yeah, I am.
You done soldering before?
A little bit.
Was it electrical or?
It was electrical.
Okay.
Have any of you taken a shop class at school?
If you haven't, say no. If you have, say yes.
No.
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 No. No.
Nope.
Okay. That's very interesting.
Yeah, good to know.
Okay, well then, we'll double up on shop classes. Let's see. Okay, moving right along. What time have we got here? We got time for a second one?
7:49.
That's what my clock says. Okay, we'll do one more here. All of the yellow brick road. See if we can't. Now there's in this particular one, some of the glue is on the outside. You can actually see it. And I'm suspecting we're going to have a problem. With the way that that adheres. So I'm going to start out with a wire brush and try to knock some of that glue off. So there's a higher probability that the solder will adhere.
You could use your file.
Yeah. Yeah. All I'm doing is creating scratches.
Yeah.
Go ahead with the flux.
Just heating it up may end up removing that glue.
Yeah, I have a hunch it'll turn black on us once it gets going. Then I may be able to knock it off. Let's get up to temp and we'll see. Okay, we got a good flow on that one. Jump over and get the other one. Good flow there. Okay, we'll just stand back and hit it with our fan. Okay, seems to have hardened up. Okay. Staying wet. Feeling cold. Good. Looks really good. Got a pretty good size dimple over on this side. Looks like a couple of them. Okay, well, rather than chase that, I am going to move right on to the third one. We'll get that one done. Okay. We seem to have enough flux left in our dish, so I'm going to go after flux. Okay. Does my audio sound like I'm gargling?
No.
Good.
Did you get new headphones?
Nope, I did not. But I'm not running some other applications simultaneously. I was hoping that maybe memory management is down. Now, I don't know if that's vulnerable, but I don't want to find out. So here we go. Okay, that one is a miss. Got a fail over the side here. Let's see if I can get it off. I don't want to change the dimensions of 40 millimeters. I'm going to make sure that we don't exceed that. Got a good solder joint there. We just good. All right. Is this too bouncy, or are you guys all watching it on Google, or are you still watching it on Teams, or what?
I'm still watching on Teams.
Okay. How is the head cam working out?
It's working well.
As well.
Good, so you can actually see what's going on at any given moment in time.
Yep.
Okay, I think we're there. Copper cools much, much faster than steel. If I was welding or working with steel, I would not begin to trust this thing this quickly, because steel doesn't cool down quickly, even after you submerged it in water. Okay. Well, I think we've got some good seals. I've got one more here that I've got to catch up, but I think we've covered the ground that I wanted to tonight. Any questions?
When is the epoxy supposed to arrive?
Before the end of next week. So Wednesday, Thursday timeframe.
Okay.
My intent is I will go ahead and mount those heat coolers, and hopefully we will actually be able to bring the reactor up and do a thermal trial. We'll be running the cooling. We'll have a thermometer active. We'll throw some voltage at it that we know would ordinarily raise the temperature, and we'll just see how high up it goes at a given value.
Will the tubing for the water be in series on those?
Yes. It'll come out of the coil and then go into the water blocks, and then come out of the water block and go into the back into the return line.